Finally, we have the second picture of a black hole taken by the Event Horizon Telescope. This time, we got the supermassive black hole Sagittarius A star at the center of the Milky Way galaxy. It has been 3 years since the team released the picture of the M87 black hole for the first time ever. The Sagittarius A star is at a distance of 26,000 light years, which is very closer compared to M87, but it is also 1,000 times smaller than M87. Imaging such black holes is a Himalayan task, but the international team of more than 200 researchers from 20 different countries and data from 8 different telescopes located at different places on Earth achieved this seemingly impossible target. In this video, I'll discuss the process as well as the extreme challenges they had to face while taking this image. So without any further delay, let's get started. Black holes were first predicted in 1915 as a consequence of Einstein's theory of general relativity. They are surrounded by a boundary called an event horizon. The radius of the event horizon is known as Schwarzschild radius, which depends on the mass of the black hole. A black hole's gravity is so intense that anything, even light crossing event horizon, can never return to the outside universe. After years of study and observations, we know that black holes are common throughout the universe. Nearly every large galaxy contains at least one supermassive black hole, which weighs millions or even billions of times the mass of the Sun. The first candidate black hole was Cygnus X1, discovered by the Uhuru X-ray satellite. That discovery was followed closely by the identification of the Milky Way's supermassive black hole Sagittarius A in 1974. In order to take a picture of a black hole, the supermassive black holes are our best guess because they are much larger, which makes them much easier to image than the stellar black holes, which are smaller. Even though black holes cannot be seen because light or any signal does not come out of it, their presence can still be felt via their massive gravity. Take Sagittarius A star for example. This gravitational monster has a mass 4 million times that of the Sun. This extreme environment is the strongest gravitational field in our galaxy. Scientists have been studying the stars and their motion near this black hole for decades. They have found that the stars nearby are moving with extreme velocities, with some even closer to 10% of the speed of light. This video shows the result of the 26-year-long observation of the stars by European Southern Observatory. It reveals the effects predicted by Einstein's general relativity on the motion of a star passing through the extreme gravitational field near the supermassive black hole. So we can feel where the black hole is, but how do we see as well as take a picture of it? Well, what we can see is the shadow of the black hole. Black holes, especially the ones at the center of a galaxy, are surrounded by an enormous disk of dust and gas that is getting pulled into it. The insane friction and gravity heat up this material, and this extremely heated plasma radiates photons which are then affected by the gravity of the black hole. So when we receive the signal, the black hole appears as a dark void in a region of glowing material. But imaging the black hole is still challenging because it sits at the center of the galaxy, being obscured by the dust cloud. To overcome that, scientists switched to radio frequencies to see through the cloud. The EHT used 8 radio telescopes on the planet that could observe at a wavelength of 1.3 mm. This time they used the radio telescope at Antarctica for the first time because it has the constant view of the Sagittarius A star. When a radio telescope is pointed towards a radio source, the plane waves coming to the telescope are reflected by the dish and is received at the antenna. By the way, the waves from the source are emitting radially in every direction, but because the Earth is so far away from the source, the waves become plane waves. The image produced by the telescope will have a bright spot at the position of the radio source, and the intensity at every other position will gradually decay. This happens because while pointing directly at the source, there will be no phase difference between the signals, so there will be a constructive interference. But there is a limit to how small the telescope can detect. It is known as the diffraction limit of the telescope, which depends on its shape. Roughly, it is of the order of the ratio between wavelength and the diameter of the telescope. And here comes the most challenging issue in imaging the black hole. The black holes are small compact objects which are situated at far distances from us. Thus they appear very tiny in the sky. For example, if the sky is taken to be 180 degrees, the moon only takes up about half degree or 30 arc minutes. Divide that by 1 million and that is the angular resolution of the black holes. Any telescope on Earth is incapable of having such resolution. Now looking at the equation, we can infer that the resolution can be improved by either decreasing the wavelength or increasing the diameter. But smaller wavelengths are out of question because the dust cloud blocks most of it. So increasing the diameter seems the only option. But in order to capture the image of a black hole, we would need a telescope of the size of the planet. So the scientists used a third option. To image the black hole, they combined observations from different radio telescopes situated at different parts of Earth. The dishes observed simultaneously, effectively acting as a virtual planet-sized dish, giving them the necessary resolving power. Instead of physically receiving the signals from different dishes at an antenna, they correlated the data computationally. But how does the virtual telescope even work? To understand that, we need some knowledge of radio interferometry. The basic principle is to take two telescopes separated by some distance and observe an object simultaneously with both telescopes. The two telescopes will then catch a slightly different part of each wavefront. Now, accounting for the delay between receiving the wavefronts and adding the data together, we can have the image of the object. The resolution of the image will be the same as a new telescope with a diameter of the separated distance between the initial telescopes. But even having two telescopes will not help much. Let's say the object is directly above the two telescopes. Hence, the signal received at each telescope will not have a phase delay and we will have a constructive interference. But we will get constructive interference even if the source is at any position on the semicircular line. Also, if the source is at such position that the signal received at one antenna is one wavelength ahead of the other, we will again get constructive interference. This is true for any other integer multiple of the wavelength. The solution to this is a bunch of telescopes with different separations which enable us to mix and match the pairs and detect structures of various sizes and orientations. That's why the Event Horizon Telescope isn't just two scopes at opposite ends of the world, but a collection of several telescopes situated at different places on Earth. This enabled the scientists to have a variety of separations or baselines in order to fill in the image. This technique is called very long baseline interferometry. And this is not something new. Radio astronomers have been using it for decades. But no one before has ever achieved VLBI with a frequency able to so stunningly invade a galaxy's innermost area. This animation shows how the Event Horizon Telescope's VLBI network works. On the left is the Earth as seen by M87's black hole. As Earth rotates, different telescopes come into view. Each forms a pair with the others and their baselines are drawn in red. Now look at the right panel. The graph plots the distance between the telescopes divided by the wavelength observed. The x-axis is east-west and the y-axis is north-south. Farther from zero corresponds to a larger separation and thus a finer resolution. The 0 point at the center is the largest scale what you would see with only one telescope. Now each pair of dishes plot two dots on this graph because you can read their separation two ways, for example from A to B or from B to A. As Earth rotates, the position of the two sides relative to each other as seen by the black hole changes. For example, the telescope in Mexico crosses more distance from left to right compared to the ones in Chile. This rotation changes both the length and the orientation of the baselines, which is why the points trace arcs across the plot over time. Now how much of this swirly graph called the UV plane is filled tells astronomers the range of the scales their VLBI network can detect. If the UV plane were completely filled in with red, we would have a complete image. That, however, would take far more telescopes than we have. Now, to fill in the blanks, the scientists had to correlate the data computationally. And to make that possible, the team installed atomic clocks at each telescope which are so dependable that they will lose only about 1 second in 10 million years. These clocks mark the observations with exact timestamps. The different telescopes took petabytes of the timestamped data And the fastest way to transfer this enormous data was to store it in a hard drive and fly the hard drives back to their supercomputer facilities for image reconstruction. But the reconstruction was not an easy job either. The data came from 8 different telescopes which had a lot of noise as well as other potential errors. The scientists used a variety of algorithms to remove different types of noise from the data pipelines, including the ones caused by Earth's atmosphere. Since this was the first experiment of its kind at this level, multiple data analysis pipelines were used. But reconstructing the image had another major roadblock, which is the human bias. The scientists had a preconceived notion of what a black hole might look like, so their bias could influence the image. This is a problem because if the scientists relied too much on Einstein's theory to develop the algorithm, the image would have been something we would expect to see. And even if the actual image had a disagreement, we would lose it. To tackle this challenge, the EHD scientists were split into 4 image reconstruction teams, and each team was independently working to create a version of the black hole image using its own techniques and parameters. The teams discovered that multiple ring geometries could explain the data as well as some geometries that do not even look like ring. The main image was produced by averaging together thousands of images created using different computational methods, all of which accurately fit the EHD data. This averaged image retains features more commonly seen in the different images and suppresses features that appear infrequently. The images were clustered into 4 groups based on similar features. An averaged representative image for each of the 4 clusters is shown here. 3 of the clusters show a ring structure but with differently distributed brightness around the ring. And the 4th cluster contains images that also fit the data but do not appear ring-like. The bar graphs show the relative number of the images belonging to each cluster. Thousands of images fell into each of the first 3 clusters, while the 4th and the smallest cluster contains only few hundreds of images. The heights of the bars indicate the relative weights or contributions of each cluster to the averaged image. Finally, we get the reconstructed picture of the black hole which matches with the computer simulations of the theoretical description. But why is the image blurry? Well, although it is blurry, ironically it is also the sharpest picture ever created in history. However, there are a couple of reasons why Sagittarius A star's image is blurrier than M87's. Firstly, Sagittarius A is a small black hole compared to M87, so the matter around it is moving so fast that it completes one rotation in few minutes. This induces motion blur in the image. On the other hand, matter takes few weeks to travel around the massive M87 to complete one rotation, and this gives ample amount of time to get a clearer picture of the black hole. The second reason behind the blurred image is scattering due to dust. While taking the picture of Sagittarius A star, the telescopes were pointed towards the center of the galaxy. The huge dust cloud between us and Sagittarius A caused the photons to scatter. While in case of M87, the light came almost directly from the center, suffering less scattering than Sagittarius A star. Another important feature the images have in common are these bright blobs. We know both M87 and Sagittarius A star are spinning black holes with accretion disks. Now, due to the massive gravity of the black holes, the light from the accretion disk is bent and we can see the whole accretion disk all at once. But due to rotation, a part of the disk is coming towards us and another part is going away from us. This motion induces Doppler beaming, which makes the part coming towards us more intense than the other parts. You can think of it like a lighthouse where you get brightest light when the beam is coming towards you. However, scientists are still uncertain about the axis of rotation of Sagittarius A star, but they hope to address this in their future works. Although these findings are really phenomenal and prove Einstein right once again, still there's a long way to go for the scientists. In the upcoming years, the EHD will include more telescopes around the globe and will try to look at the black holes with different wavelengths. They also plan to take a video of the Sagittarius A star where they would be able to see the motion of the accretion disk. So we can hope for many exciting discoveries in the upcoming years. And who knows, some even might be able to change our concept of the universe forever. Thank you for watching. I hope you liked it. Please share your thoughts or doubts in the comment section. If you want an in-depth analysis on this or want to suggest some topics I should cover next time, please feel free to comment that as well. And please don't forget to subscribe for more videos like this.